Jai Hind everyone. My name is Ankita Rani. I am working as an assistant professor in the Department of Computer Science and Engineering in Ajay Kumar Garg Engineering College, Ghaziabad. So today we discuss the topic Fitts Law, and this topic comes under the subject Human Computer Interface, and the subject code is KCS 058. So now let's understand what is Fitts Law. So Fitts law is basically given by the Paul Fitts, and the date of birth of Paul Fitts is 1912 to 1965. So Fitts law or Fitts law name is given by the Paul Fitts for his 1954 study of pointing. So in this law we study about the pointing. So Paul Fitts study uh, of how to pointing a device, of how the movement time between the cursor and the object. So his original study was on pointing with a stylus. So now you can see that this is the stylus experiment. Through this experiment, Paul Fitts can do the study of pointing in the year 1954. So, but his work is applicable to pointing with a mouse using touch screens and the range of pointing devices for 2D display. So, Fitts law mainly work for the touch screens and not for the like buttons, and this is also work for the mouse, because mouse, touch screen and scanner, these all are the pointing devices, and the range of the pointing devices for 2D displays. So Fitts law state that the amount of time required for a person to move a pointer to a target area is a function of the distance to the target divided by the size of the target. So basically the formula of Fitts law is that Fitts law is the distance upon size of the target. Distance upon size of the target. So in Fitts law, the distance of the target and the size of the target. So thus the longer the distance and smaller the target size, the longer it takes. For example, in a computer screen, there is a mouse and there is a if the smaller object, then the movement time between the cursor and the object is more, and if the object size is small, then the movement time between the cursor and the object is less, because the object size is very big. So we recognize the object very quickly, and if the object size is small, so we have some problem in recognizing the object in the screen. So in 1954, psychologist Paul Fitts, examining the human motor system, showed that the time required to move to a target depends on the distance to it. So basically the Fitts law is directly proportional to the distance, and the Fitts law is inversely proportional to the size of the target. So yet relate inversely to its size. So by his law, fast movement and small target result in greater error rates due to the speed accuracy trade-off. Although multiple variant of Fitts law exist, all encompasses the idea. So there are the some also other variants comes in the Fitts law. So this law is given by the Paul Fitts. So in 1954, a psychologist named Paul Fitts created a predictive model that describe how quickly pupil can select a target. So suppose this is our cursor and this is our object. So how much time it will take to reach the target? So this time is calculated by the Fitts law. This is the Fitts law. In Fitts law, we calculate the movement time. So our target is what the user is trying to interact with. User trying to click some icon, trying to click some object. So it could be a button to tap or a form field that needs to be clicked into. This model is commonly used in human computer interaction. For example, when you are searching in a Google, or when you are open some mails through the Gmail, so there are the two options like sign in or sign up. So both the options are placed nearly together. So we can predict that this button is near to each other. So Fitts law establishes that the further away a target is and the smaller the size of the target, the longer it takes for a user to acquire. So if the size is small, then the target is we can difficulty achieve the target. So and if the size is large, we can easily achieve our target. So large target that are close by have the lowest interaction cost, while small target that far away have the highest interaction cost. So if our target is large, if the target size is large, then the interaction cost is low. Otherwise, if we have the target size is small, then the interaction cost is high. So after that, we have to know what is an interaction cost. So interaction cost is nothing else. Interaction cost is this, how the pupil interact with the cursor, with the object in the screen. So the Nelson Norman group defines interaction cost as the sum of efforts, mental and physical, that the user must deploy in interacting with the site to reach their goals. So interaction cost is nothing but the sum of efforts, the efforts which is taken by the person, which is both the mentally effort and the both physical effort, because mentally effort the user can recognize the object, and physically the hand movement of the user. So this is the interaction cost. So if a user can find an answer they are looking for without needing to scroll, tap or explore, they are experiencing zero interaction cost. For example, if the user want some icon or want some object, and they will get this object very quickly, and they do not work hard for that object, so this is so the cost is zero interaction cost, because the user does not need to scroll the page, does not need to tap some other icons, and does not need to explore. So in this case they are experiencing the zero interaction cost. But if a user has to locate a menu, has to find some location, has to find some icons, and the user scroll through over a dozen options, means the user needs scrolling of page, vertically scrolling, horizontally scrolling, and click a small button to complete their form. So that's going to be a higher interaction cost, because in this the user perform all the tasks like locate a menu or scroll a page, click a small button, the object size is small, and the user find difficulty in find difficulty in finding the object. So this takes a higher interaction cost. So ideally, UX and UI designers aim to make these costs as low as possible, because the lower the interaction cost, the better the usability of their app. Lower interaction cost means our page is simple and small page, like in the page there are no some options, like the page is not complicated. So if the cost is low, then the better the usability of their app. uh, the novice person, new users can easily use their app, because the app is very simple and easy to understand. Designers can minimize interaction cost by following Fitts law and minimizing reading, scrolling, clicking, typing, waiting for pages to load, and attention switches, memory load, and exploring to find relevant information. So we can decrease the interaction cost by using the Fitts law, because Fitts law is helping in calculating the movement time for reading, calculating the movement time for scrolling, for clicking, typing, and waiting for pages to load. So these all are things can be minimized through the Fitts law. And our interaction cost is also low with the help of the Fitts law. So this is the example of how to perform Fitts law. Suppose this is a cursor and this is the our object. So in this, the object size is big, and similarly in the second image, this is our cursor and this is the object. So in second image, the object size is small. Here the object size is small and here the object size is large. So this object can be icon on the image, like for example icon. Object can be anything like icon, like some button, submit button in the form. So icon can so the object can be anything. So these are the two cases. So if we have a large size object, then we can recognize the object in the screen very easily, because this object is clearly visible to every user in the screen. If the size of the object is small, then the user can find difficulty in recognizing the object, because in screen there are multiple icons, there are multiple objects, multiple buttons. So a smaller object partially hidden with the other object. So obviously it takes some more time, because this is the distance which we can this is the movement time which we take uh, which we take to the movement cursor to the object, and this is the time which we take through the cursor to the object. So through the figure easily show that it will take the less time and it will take the more time. So Fitts law tells us how long it will take to move a pointer from a specific position to hit different targets. So through the Fitts law we can calculate this time, and through the Fitts law we can calculate this time. So basically Fitts law is for the calculating the movement time between the cursor and between the object. This is called Fitts law. So the targets that are larger and closer and are easier to hit than ones that are smaller and further away, because larger targets can easily visible to the user. We can use Fitts law to predict how long it will take to hit a target or series of targets. So the hitting time uh, can easily calculated with the help of the Fitts law. We can also use Fitts law to compare different input devices. So if you are using the different input devices like keyboard and mouse, so we can also use the different input devices. So we can also calculate the time which will take through the mouse, the time take to the pointing devices. So this is the another example. So in this figure, icon second is bigger because it has text below it. Icon second is bigger. It is clearly shown, and the text is also written in the image second. And icon second will therefore be slightly quicker to hit, because in this image this size is big as compared to this size, and also there is a text written in that object. So this is the image 2 is easily to hit the target. However, icon second is only larger on a vertical axis. It will not be any quicker to hit than icon 1 when moving horizontally. So in image this is clearly shown that this size is small and this size is large, because it has text in it, because there are some icons on the screen which we have a name. So this is the cursor. So this is the another example of Fitts law. So this is the equation of the Fitts law. MT is equal to A plus B into ID. This is the most important formula, or this is the most important equation of Fitts law. Here MT is the movement time, typically in milliseconds. Movement time are that time in which we take uh, through the cursor to the object, and here A is the intercept and B is the slope. This is the slope, and ID is the index of difficulty. So in this, MT is movement time is typically given in the milliseconds. The time can be like 396 milliseconds, 100 milliseconds. It will take to the cursor to the object, and A is the intercept and B is the slope and ID is index of difficulty. So this is the graph of Fitts law. In this, this is the index of difficulty, and at here this is the movement time, and this is the slope which we use in the Fitts law. So there is a linear relationship between the movement time and the index of difficulty. So this relationship is shown through that graph. This is a linear relationship. So in this graph, we can easily show that the relationship between the movement time and index of difficulty is a linear relationship. So when comparing different pointing devices, A and B can be experimentally determined. So in this, we can say that A is the like one device and B is the another device. So A is the one object and B is the another object. So when predicting how quickly a target can be hit, A and B can be assigned a value. So if you are predicting some value, or if you are hitting the target, then we can easily assign a value, or in a question we can give in the value. So first of all, before calculating the equation, we must know about the ID, index of difficulty. Means how we can calculate the index of difficulty. So the index of difficulty can be expressed in several ways. So the following is an ISO standard. Index of difficulty is given by the ISO standard 924129 for the ID. So it is also known as a Shannon formulation. Index of difficulty also called as Shannon formulation, because this formula is also called as Shannon formulation formula. So in that the formula is ID is equal to log base 2 D divided by W plus 1. Here D is the distance to midpoint of target and W is the width of the target. So previously I told you that Fitts law is nothing else but distance upon size. So distance here is the D and size is the width of target. So size is the W. So this is the Fitts law. So for calculating the distance and for calculating the size of the target, we need the ID, index of difficulty. So in this figure, this is the cursor and this is the object. So the distance is nothing but the time it will take to reach the object. Distance is the time through which the cursor can reach to the object. So this is the distance time, and W is the size of target. So this is our target, this is our object. So this is the width of the target. So when we know about the width of the target and distance of the target. So we can easily calculate the index of difficulty. So if so after we putting it all together, we can easily calculate the movement time between the cursor and the object. So this is the equation of Fitt's law. Mt is equal to a plus b log 2 d divided by w plus 1. So assume a, let's assume a is equal to 50 milliseconds and b is equal to 150 milliseconds, and this is the image 1 and this is the image second. So you can clearly see that the in image 1 our object size is large as compared to the object size in image second. This is the object size and this is our cursor. So in this diagram you can clearly see that the distance between the cursor and the object is less, and in the second figure this is the cursor and this is the object. So in this figure you can clearly see that the distance between the cursor and the object is less because this is the cursor and this is the object. So in first figure the distance between the cursor and the object is 80 mm, and in second image the distance between the cursor and the object is 100 mm. So we can put this value in the formula. Similarly, for the object, in object the width of the target is 20 mm, and for the second image the width of the target is 10 mm. So all these values we can put in the formula. So like for calculating image 1, this is for the image 1. Let's assume a is equal to 50. A is, we can put here this value like a is equal to 50 plus at on the position of v we can put the 150. So b 150 log base 2. D is the distance. So distance in image 1 is 80 millimeter, 80 mm, and divided by W. So the W is equal to 20 mm. So by calculating this, we can get this time 398 millisecond because movement time is calculated in the milliseconds. So 398 milliseconds is that it will take 398 millisecond for reaching the cursor to the object. So similarly in the for the second image, this is for the second image. Let's assume the value of A value is 50 and let's assume the value of B is 150 log base 2. The distance of for the second image is 100 mm. So we can write here 100, and the width of the target for the second image is 10 mm. So we can write here 10. So by calculating this we can get 569 milliseconds. So this is the movement time for second image. So 569 milliseconds it will take for reaching the cursor to the object. So this is the formula for calculating the value of the Fitt's law, because this is the equation of Fitt's law. Through this we can easily get the movement time between the cursor and object on any screen. So with this formula you can easily find out the movement time of any movement in the screen, any movement between the cursor of clicking the button, between the cursor to clicking a button, clicking a icon. So with the help of this formula you can easily get the movement time. So physically interpreted, Fitt's law state the following. So there are some interpretations of the Fitt's law which we have stated, like big targets at close distance are acquired faster than smaller targets, at long range. So previously I told you that for the is a larger object we can easily calculate the distance is less, and for the smaller target the distance is large. So index of difficulty provides a single combined measure of two main physical properties, movement, task. So basically index of difficulty provides a uh, measure for calculating the physical properties of the movement task, because because id provides the value of the a and b object of two objects. Id increases by 1 unit for each doubling of amplitude and halving of width. So we can increase the value of index of difficulty by 1 unit for doubling the amplitude and halving the width of the target. So positive intercept indicates additive factors unrelated to ID. ID is index of difficulty. So it can be calculated or it can be related to mechanism of movement or selection. Selection like mouse button, etc. So this is for the selection and movement. So with the help of the mouse you can or with the help of the button you can select the movement or selection. So there are the some scope of Fitts law, and there are some applications of Fitts law. So Fitts law is an effective quantitative method of modeling user performance in rapid aimed movement, where one appendage like our hand start at rest at a specific start position and moves to rest within a target area. For example, at this position we have a hand of the user, and this is our object, and this is our object. So in at this position user can reach, so this is the movement time. So we have to calculate this time. So the law can be used to assist in the design of user interface and evaluation of alternative task method in graphical user interface. So like for example, the designing of the user interface and the evaluation of the task which we performed through the user in graphical user interface, this law can be used for can be used to assist in the designing. So it can also be used to predict the performance of operators, like performance of operator in a user adaptive system. And this law can also be used to assist the design of user interfaces. This law is not only for calculating the movement time, like you can see that this law can also be used for designing of interface, and this law can also be used to predict the performance of operators in a user adaptive system, assist in allocating tasks to operator, and this law can also be used to predict movement time for the assembly line work. So these are the three main basic applications of the Fitts law: designing of user interface and the evaluation of alternative task method. And the second thing is performance of operator, and the third thing is predict the movement time for the assembly of work. So these are the scope areas in which we apply the Fitts law. So there are the some principles of Fitts law which we have to follow these principles while using the Fitts law. So theoretically the following principles exist when applying Fitts law to interface design. So before we applying the Fitts law in the human computer interaction, we have to follow these principles, or we have to keep in mind these principles while using the Fitts law. So our first principle is things done more often should be assigned a larger button. So the things can be done more oftenly if you are assigning a large button. So this seems an intuitive principle, but it needs to be used very carefully since it harms the consistency of the interface. So, in this, this seems an intuitive principle. Like this principle is very important, but it need to be used very carefully because it harm the consistency of the interface. So we have to also maintain the consistency of the interface. So things done more often should be closer to the average position of the user's cursor. The amplitude of a widget allow more control from interface designer compared to the width. Again, this needs to be used with caution since frequency based widget arrangement may slow down the user from finding things compared to logic based arrangement. So, this is the second principle which we have to follow, and this is the first principle which we have to follow. The third principle is the top, bottom and sides of the screen are infinitely targetable because the boundary created by the edges of the screen are unless a virtual screen exists. So, in the top of the screen and bottom of the screen, side of the screen are infinitely targetable, means in the screen you can put the icons in every corner of the screen and anywhere on the screen. They should be fully utilized. So we have to use the fully screen area. So this is the third principle which we have to kept in the mind while using the Fitts law. Second is, so these are the three principles which we have to kept in mind. So there are trade-off when applying Fitts law to interface design. What are these trade-off? Fitts law suggests that interface components should be made larger and positioned closer to the average cursor position. So this is the trade-off which provided by the Fitts law. These suggestions may act in opposition to other factors that make an efficient interface such as organization and use of available screen space. So these are the principles which we have to keep in mind while using the Fitts law. So this is the example of Fitts law. This is the cursor and this is the magic pixel and this is the pop-up menu. So as an example of using Fitts law to assist user interface design, consider the invention of interface widgets such as pop-up menus, like this pop-up menu. So given, for example, given a large 1600 by 1200 screen, where should a target be placed so that the user can access it fastest no matter where the user is originally located. So if you have this screen area like 1600 by 1200, the user can confused where to put the cursor, where to put the icon. So Fitts law says that for a fixed size target, the acquisition time decreases when the amplitude of movement decreases. So the fastest pixel is located right at the current location of the mouse pointer. So in this we can put at the right of the screen. So pop-up menus makes use of this magic pixel showing up relative to the mouse pointer. No matter where the user may have moved it, the pixel requires zero travel and is in effect an infinitely large target, so it just cannot be missed. So with the help of this magic pixel, they can tell the user of how to put the cursor in the large screen area. So thank you, student.